Alright, let's dive into today's second class where we will cover something fundamental, the relational model and the relational algebra. Why are these concepts important? Well, they serve as the blueprint for designing common relational databases. Today's lesson is structured to provide a comprehensive understanding of these topics. We will start with the relational model and the relational algebra. For those of you who have a background in computer science or related fields like set theory or graph theory, this content should feel familiar. We'll spend about 30 minutes discussing the basics, including common operations in relational algebra, which are actually quite straightforward. Feel free to interrupt with any questions during the Q&A session later on. Let's get started. The relational model has been around since the early days. First proposed in 1970 by Tackott, is outlined in a well-known paper and has since become a cornerstone in database theory. Tackott emphasized that three key characteristics of the relational model: simplicity in data structures. Databases are stored in simple data structures, relations, done. Data is accessed through high-level languages. Physical storage is delegated to the implementation, remaining transparent to upper-layer applications. This model laid the groundwork for modern database management systems, like DB2 and Oracle. Despite its age, it remains highly relevant today, providing a structured approach to database design and management. Today, we will dive into the concept of data models, focusing on the conceptual model. A data model defines the structure and the organization of data within a database. It's essential for understanding how data is organized and presented. There are various data models, such as the relational model proposed in 1970, which forms the basis of many relational databases like Oracle and DB2. Other models include key-value stores, graph databases, and document databases, each tailored to specific data storage needs. We'll primarily focus on the relational model in today's discussion, exploring its characteristics and construction methods. Let's dive in. The relational model has three main characteristics. Firstly, let's talk about structure, which refers to the definition of content within. This includes attributes a relationship has and values contained in those attributes. For example, if we have a relationship with three attributes, it's just what we are talking about. For instance, let's consider a relationship involving a singer, like artist. In this singer-artist relationship, there is an attribute called name, referring to the singer's name, along with the debut type and nationality. These attributes can also include professions. For example, a name could be any subtitle in English or Chinese, such as Fei Ye Wang, Yi Sen Chen, Zhei Chou. Moreover, when referring to the year, it's likely just indicating that this four-digit numerical can have a specific value. Additionally, this integrity also pertains to guaranteeing that the data satisfy these restrictions. For instance, as I previously stated, the year must be a numerical, and the name of the vocalist cannot contain any special characters. Certainly, there might currently exist certain instances, however, during the execution of this type of rigorous validation, we will encounter this restriction condition. constraints, which encompasses various operations. In other words, how do we gain entry to and make changes to data within this relational model? This represents one of the three principal attributes of the relational model. Speaking of the relational model, first of all, let's talk about what a relationship is. It's actually an ordered collection that represents the connections between entity attributes. Because relationships are unordered, they can be stored in any way. And optimizing this storage method means deciding whether to use row storage, column storage, row-column hybrid storage, including other strange ways. Actually, any way is possible. Then we can optimize it further inside. So what is the actual relationship? If you were to map it to this relational database, or if you want a more intuitive understanding, especially just the table and all the legal data inside and outside the table, such as the table on the right is actually a relationship with the addition of its data to the tuple. In other words, you can imagine as a row of data in a table in the database. It is a collection of attribute values in this relationship. Originally, this value must be atomic, that is, it has atomicity, or it is a standard quantity. Its definition is very clear. Now, this value can be nested value in JSON. You can also store actual data in it. In fact, it's the concept of expanding attributes of this tuple in database development. Each attribute can also be stored. That is just me having an empty attribute. It means that this attribute is not defined. For instance, in my country, it can actually be empty, indicating that this attribute is defined in mathematical terms. It means that each element in my Cartesian coordinate system, referring it as an n-tuple, is essentially envisioning it as a row in a table within a database, encompassing its data. If you desire a more intuitive manner to visualize and comprehend the concept, let's move on to the next topic, which is actually quite easy to understand. In a database, everyone knows that if an attribute of a relationship uniquely identifies a tuple, it's called the primary key. Generally, identifiers are used as primary keys because common attributes like names can have a duplicate. For example, there could be multiple people named Zhang Liang, or historical figures and current individuals sharing the same name, making it difficult to distinguish between them without a unique identifier. In a national database or any relational system, everyone's identification number serves as a unique identifier. This unique identifier can then be used as the primary key. In SQL 2003, for example, sequence, a keyword for primary key, and in MySQL, auto increment is a component primary key used to automatically increment this identifier, which helps clearly distinguish individuals, like 101 for Fei Wang, 102 for Yisun Chen, and 103 for Jay Chou, turning these identifiers into unique primary keys. Additionally, there is a concept of a foreign key. A foreign key refers to an attribute in one relationship that must map to tuples in another relationship. For example, my attribute can refer to an attribute in another table, which constitute a foreign key. For instance, while artist ID 101 might lead us to Fei Wang, if you attended the previous class, you would know about the album Stranger Under My Skin from 2011, co-created by Ethan Chen and Fei Wang. This makes it difficult to ensure the uniqueness and validity of just one album ID, such as having both 101 and 102. To solve this, we create a mapping table between artist and album, which contains two keys. One is the foreign key corresponding to the artist, and the other is album ID, mapping to the album as another key, foreign key. For example, album number 12 could list both 101 and 102, indicating both Fei Wang and Ethan Chen contributed to it. This table allows the foreign key to correspond both to the artist and the album. For instance, ID 103 shows that the artist is Jay Chou, with the corresponding album ID 13 from the year 2000. While primary key in one table is referenced as an attribute in another table, it automatically becomes a foreign key. This is crucial because these primary and foreign keys often appear together, allowing for complex relational queries. In some databases, this situation naturally leads to a join between the two tables, improving the reading speed by storing the joined result as tuples or combining them in a way. In the next lesson, we'll explore how disks handle these configurations and how tuples are processed. We are going to define something within this relational model. We are going to define a database manipulation language, or DML for short. This DML is designed to access objects and data within the database using a programming language. There are two types of DML. These two types that do not coexist. The first type is procedure. This means that, for instance, the query specifies the DMS search strategy. The second type is non-procedure. This simply specifies what data is needed without defining the process of how it's fetched. SQL is a non-procedural DML. You specify what you need. For example, get an ID and a name from a table, but you don't manage how the system retrieves it. This approach is more typical of high-level languages, which are generally non-procedural and abstract away the underlying physical and disk operations. When designing a DBMS, we must consider these operations and optimize them for the front-end scenarios we are addressing. This involves deciding on a storage model, whether it is row-based, column-based, or some other method, and how to optimize this data storage method based on the specific scenario and data types involved. Lastly, I mentioned that the relational model being independent of any specific query language implementation. If we don't have a DML or if we don't have a DBMS, but I have a file and a bunch of data. In essence, this is a simple database. Earlier, when we defined the database, we said a database is just a set of entities. Let's take a look at the table on the right. We can query the data via Python script. First, we go through each line of file and assign the content to an array. When we find out the first element of the array is Jay Chou, we then print out its second element accordingly. For example, you can also use SQL to select data within a query like select year from artist where name equals to Jay Chou, which illustrates how SQL can operate independently from programming languages, making it easier for various programming environments to use SQL effectively within their systems. As you can tell, users can use any programming languages such as Java, Go to query the data via SQL. This is the separation of concern. We'll talk extensive about the relational model. So from now on, all the remaining topics are actually quite straightforward. If you have studied concepts like set theory, graph theory, or discrete mathematics, you shouldn't have any trouble understanding the corresponding content in discrete mathematics. For example, in our specific scenario, relational algebra is used to retrieve and manipulate fundamental operations in tuples. And each operation will involve one or more relations. When given an output, it will form a new relationship. Basically, these relational algebra operations are translated to the final SQL to perform an operation on this database. In terms of relational databases, for example, like this select, update, and so on, are all this kind of cross-join, outer join. What is it actually? It goes back to its most fundamental level. Actually, it's about relational algebra. For example, first of all is select. In reality, it is actually a symbol of sigma. It signifies that the select represents the process of inputting a relationship and outputting all tuples that satisfy a specific predicate. And this specific predicate functions as a filter. Furthermore, we have the ability to use conjunctions and logical words to enter multiple predicates. It is truly simple and straightforward, as you already know. It's quite simple, really. We are learning SQL, and generally speaking, it will be just select star from R. This R represents the original relation. And when I provide input R, it signifies that R represents a relationship. For example, within this relationship, A ID equals to A2. This N is a conjunction. A logical word indicating N, such as B is greater than 102. This is a select operation. Typically, we denote projection as a pi. It essentially takes a relation as an input and output tuples that only contain specific attribute. This means that instead of using select star, which selects all tuples, projection mirrors the functionality of select, but it strictly output all tuples that include specific attributes. For instance, if I have attribute a underscore ID and b underscore ID, within this relation R, I set a underscore ID equals to A2, it will output. Furthermore, it allows for the reordering of attribute in the output relation. If I specify the order as b underscore ID, a underscore ID, then what it prints or projects in the end will be a b underscore ID 102, a underscore ID A2, b underscore ID 103, a underscore ID A2, thus performing such an operation. Essentially, this corresponds to the SQL command select attribute names from relation or table, where specific conditions are set. The union operation means that I input two relationships and output one relationship. The input relationship must have the same attribute value. So what this means is that my operation of doing a union is to find a common attribute value in the two input relationships. For example, after performing this union on R and S, it actually corresponds to combining the tuples from R and S that have the same attribute values and creating a new relationship with those combined tuples. In the database, the operation is originally select star from R, and then a corresponding operation union all select star from S is performed. And then it is combined together. And the result will be A1 101, A2 102, A3 103, and then another A3 103 because it overlaps with the previous one, essentially becoming a single data entry. Then A4 104, A5 105. This forms a new relation, which is essentially a union. And this intersection is even simpler. I need to find the intersection of R and S, and input the tuples that appears in both relations into a new relation. This tuple should appear in both relation A and relation B, as well as relation R and relation S. Additionally, the input relations must have the same attributes. I'm looking for A1, but A1 isn't there. Not in A2, but A3 is present. If A3 is present, then 103 should also be present. We don't have this A4. A5 is not available, but I found A3 and 103. They appear in both R and S, and they have the same attribute. So let's find it. The new relationship is AID equals A3, and BID equals 103. In SQL, the operation would be intersect, as in select star from R, is intersect select star from S. This operation corresponds to finding the intersection of a relationship. There's also the difference operation. It involves inputting two relations and output a relation that includes all tuple that appears in the first relation, but not in the second. That essentially forms a complementary relation. For example, with R minus S, select star from R except select star from S. The result will be the tuples that appear in R, but not input into S. Let's find an example. If A3 appears here, I'll remove it. Thus, the result would be A1 1, A2 102, but conversely, the operation changes. S minus R means the tuples that appears in S, but to be removed if they are also appeared in R, forming another complementary relation. So the final output will be A4 104, A5 105 appear in S, and since A3 103 is already R, it is excluded, resulting in such an outcome. As you can see from the SQL I write, it involves an except operation. Then there is a product operation. This is derived from the condition product, where I input two relations. It automatically outputs a relation that contains all possible combinations of the input tuples. What are all possible combinations? It is the multiplicative relation, where I use this relation to multiply that relation. For instance, if A1 multiplies this relation, it will perform a cross join with A3 which is this kind of multiplication relation. This kind of join connection, after initially connection, it will combine A1 with V3 the A1 with A4 and then A1 with A5 totally 3 plus 3 times 3, which is 9 times of the tuple combinations in total. In this database, I can perform this using two operations. One is cross-join, using R cross-joins, RS. Another simpler method is select star from R S, where the common S can integrate R and S. This output input includes all these combinations and select them out. And finally, there is a join operation, where we talk about joins. What we are referring to is typically the natural join. A natural join actually creates a relationship of tuples. Each combination of every input relation that shares multiple common attribute values come into play. For instance, in the relationship R and S, only the tuple A313 is common in both R and S, and it shares these attribute values. Thus, automatically, we select it out using select star from R natural join S. In practice, this join operation involves inputting two relations and then outputting one relation that contains all tuples. These tuples are combinations of two tuples that shares each attribute, and the attribute values of these two tuples must be the same. Therefore, it forms a natural relationship. This join is essentially a very common operation. Typically, it involves using what we initially discussed, a foreign key, to perform a related operation through relational algebra. In summary, it is a procedural language that represents a high-level depiction of how to query, focusing more on the data model and the structure for representation. For example, if I perform an operation join R and S, whether I join R and S first and then select, or I select first and then join, both expressions will yield the same result. From a top-level design perspective, it represents a high-level query formulation. However, sometimes the order of operations can vary. For instance, performing a join first might be very costly because it involves two full table scans to make the related connections. Then performing a select. If the select is done first, it might only need to pull one or two data points from a table, which would make the join much faster. Thus, in top-level design, we consider how this procedural language will operate, whether to make a set larger or smaller, and perform related content operation effectively. The better approach is to describe the desired outcome, and then the DBMS calculate based on this result. This capability of SQL makes it a standard in relational databases. So when mapping from SQL to how we decompose this SQL and finally operate on the disk, we also need to consider it, because as we know, disk speed is very slow. We need to thoroughly consider how to avoid this related read-write I/O issues in the design to make it more relational. That covers all the content for today's lecture. Thank you, everyone. As you all know, CnosDB Cloud is alive. And welcome to join our Discord channel, and please feel free to discuss or raise any issue if you encounter. Thank you very much. See you next time. Bye-bye.